Hi everybody, welcome back to Chem 121. This is the last lecture before midterm number 1. It's not the last time we're going to meet because we have a review session tomorrow, so don't forget about that. I'll send out an announcement tonight about what that entails. There is not really much that you have to do on your part with regards to a review session other than bringing me questions because I don't prepare them ahead of time. It actually takes a lot of time to write good questions, which is why textbooks are so expensive. You're basically paying for their time. So I can't. It's hard for me to make stuff up on the fly. Like I could do like 2 or 3 good questions in an hour, and you don't want to sit here while oh well, let me do this calculation and try that. Like that's not the point. So bring any questions that you might have either from the textbook or a worksheet or some other place or whatever. And then type them into the chat and I will be able to do them. You can also send me a picture on Discord. I will just keep a bunch of pictures that say, like, solve these questions or whatever. Last call for quiz number 3 is tonight. It will close at midnight, so make sure that you get that in before it does. And then finally, quiz number 4 and lab worksheet number 2 are due tonight as well. Those close tomorrow, so if you still have quiz number 3, and you haven't already done quiz number 4 or lab worksheet number 2, you at least have 24 hours to turn in the 4th quiz and the lab worksheet. So, all right. I did skip some slides here on the presentation here. So if I zoom out, we ended here. This is where we stopped. These next few slides here are just like, hey, it's more of the same. We've already talked about how to draw a Lewis structure for polyatomic ions. So I'm sort of skipping ahead of this because it's not really that much extra. There's some extra practice problems for you to try that particularly deal with polyatomic ions. So definitely do those for practice, but in the interest of time, I need to keep going because we need to get through this content today. These topics are not super long, but they're pretty involved. And in fact, one of them requires me to get a website out. And I didn't do that, so let me do that really quickly. This website is actually in... It's actually in the lab worksheets. It's lab worksheet number 3, which is relevant to what we're about to do, and that may actually help you study. But I'm going to post this link here. That I'm going to be using in just a second. And then I'm actually going to... Oops, I got to move this over here. Let's see here. No, actually, I don't need to do that for this class. That link that I sent you is the only one that we're really going to need today. So, assuming it loads, because if it's Flash, it might not load anymore. Perfect. Okay, cool. All right, so I have that ready for when we get to that. Okay. All right, so the first thing that we're going to talk about in the geometry section is that molecules aren't flat on paper like we've been drawing them. I mentioned it yesterday at the towards the end of the stream that if you are a molecule that was completely two-dimensional, then the resulting structure would also be two-dimensional. And while you could probably think of some other ways, like, oh, well, molecules can exist in 2D but then be 3D. Sure, they could, but it's a lot easier to just have a molecule be 3D in the first place. And there are actually a lot of reasons why that is that we're going to find out today. And they're going to be very, very obvious, like, oh, duh, that's a logical conclusion about how that works, sort of thing. And that's encapsulated in this acronym that you see at the top here, VSEPR, or Vesper. We're going to talk about what that means in just a second. But the premise behind today's lecture is that molecules aren't flat. They exist in 3 dimensions, just like we do, just like everything else does. And you can figure out what their actual shape is going to be based on the Lewis structure that you now know how to draw. Now, drawing a Lewis structure is not trivial, I would say, but it's something that you can do reliably 99% of the time at this point already. And if you draw your Lewis structure correctly, you can then predict its geometry in space. So you can see this molecule in the back here. If I were to take my pen and write out its formula, because that seems like something that'd be interesting. So if I wrote this, so there's the formula of this molecule. And if I was going to draw its Lewis structure, I'm going to just draw this real quick for you because I have done this forever. So I could just do the Lewis structure without actually having to do all the rules there. This is what this molecule looks like. Excuse me. Now, if you look at that on paper, you might be inclined to say, oh, all of those atoms in the middle are on a straight line. The H connects to a C, connects to a C, connects to an N, connects to an H. But if I draw that on the board here, you'll notice that that's not a straight line at all. No matter how you, turn that, it's not going to be a perfectly straight line. It might appear to be a straight line due to perspective, but it won't actually be a straight line like we have implied in our diagram here. So our Lewis structure is great for telling us how the atoms are connected, what's connected to what's connected to what, but it doesn't do a great job at telling us how does a molecule actually exist in three-dimensional space. Now, you might be asking yourself, well, why the hell do I care about what the molecule shape is? I mean, getting its general structure is good enough, right? When you get to biology and we talk about enzymes, shape is the big thing. Because an enzyme has a specific shape, right? And in order for a molecule to work, it has to fit inside that shape. And if the molecule has the wrong size or orientation in space, it's going to go into the enzyme active site and kind of just bonk off of it. Oh, it doesn't fit. I can't get the reaction to go. And this can have some very interesting effects. We talk about a few of those in 131, but you'll talk about this in more detail in bio. Things like enzyme inhibition or how poisons work, where they bind active sites that are necessary for your bodily function. Or even how medicine works. So, like serotonin and dopamine, not inhibitors, but well, maybe, I don't know. Those molecules binding to specific active sites literally make you happy. That's how happiness works, is molecules binding to a specific active site. Stuff like that. So shape is actually very important, and that's what we're going to talk about today. So, now, the first question that we're going to ask us is how does this work? If I know the Lewis structure of a molecule, how the heck do I figure out its geometry? And the answer to that is surprisingly simple. If matter takes up space, like we discussed at the very beginning of the class, what will that matter do when it encounters other similar matter? And the answer is primarily, well, matter isn't primarily electrons, but in terms of volume and what has the most influence, electrons exhibit a charge. And so, because they're so far from the nucleus, basically the way that atoms have to, quote, communicate with each other is through electrons. What do we know about electrons? Well, they have a negative charge. And what will two electrons do if they encounter each other? Hopefully you're all like, repel, let's repel, and you're typing it in right now. But yeah, electrons will repel each other. Now, my discussion here has to do with electrons from different atoms, but if the electrons are from the same atom, they still repel each other, right? This is the premise behind why I didn't draw a Lewis structure like this. What will my electrons do if I try to pair them together? But there's all this space over here. Well, these guys will get repelled such that they have spaced out as evenly as they can. So we've already sort of been doing this. This is why we did one dot per side before we paired them if we had to. Now, when you make bonds, the same thing happens. If I made CH4, this is not what would happen. My molecule would not look like this, because these electrons would all repel each other. And so this is not a shape that we would see. Instead, all those bonds would push apart because the bonds contain electrons. And they would spread out around the carbon in the orientation that gives you the most possible space between them. In other words, something like this, right? Where I have the maximum angles possible. Now, again, my picture is a little deceptive, but we're going to talk about that in a second. So the entire premise behind geometry and how it works, and the whole thing that you want to keep telling yourself today, kind of like a mantra, bonds have electrons, and electron pairs are electrons, and they repel each other. And they're going to repel each other until they are as far apart as humanly possible, or atomly possible, I guess. This is the premise behind Vesper Theory, also known as valence shell electron pair repulsion theory. I'm saying that on purpose really quickly to make it sound intimidating, but in reality, it makes sense. We know all of these terms. So valence shell, these are the electrons that we are working with because they live on the outside of the atom. Electron pair, all the electrons are paired either as a bond or as a non-bonding electron pair. And then repulsion, electrons repel. And then the word theory basically just means, hey, we understand this at a very high level of detail. That does not mean it is false. That is a colloquialism and a misuse of the word theory. So we're going to call this Vesper. Vesper theory basically says there is a given configuration for a molecule's geometry depending on the number of electrons around its outside. How does that work? It works in the following way. First, we're going to consider what possible things take up space around our atom. I'm going to call our atom, in this case, the central atom, because we're going to put the nucleus of it in the center of our structure. So I'm going to put both things on here, and I'm going to draw them on this screen right here. Oops, that's no good. There we go. And, oh, I was playing around in Photoshop yesterday, and I had to use different colors, so I'm going to turn that off of, like, pale gray that you can't see. So I'm going to draw my atom here, and I'm just going to call it X. Oops, that's not a pen. That's the select tool. I also made my pen size really small because I was doing detail work. There we go. That's better. Okay. So I'm going to draw my atom here, X. And what I'm going to do is I'm going to put a pair of electrons up here and then some bonds. And I'm just going to call these other atoms H. And you'll notice that I have pushed all three electron regions as far apart as possible. I'm going to take my pen and I'm going to circle where the electrons are. So I'm going to circle one here. Bonding electrons. I got to close this window here because it's going to keep popping up at me. I have electrons that are also here. Those are also bonding electrons. And then I have electrons up here. I have this non-bonding pair. And then what I'm going to do is I'm going to count, okay, how many different places did I circle electrons? And so I would say, well, there were 1, 2, 3. So what I'm going to do is I'm going to say there are 3 places with electrons. And what I'm going to call these is 3 electron groups. So when we're talking about geometry, we're going to be calling these locations where electrons exist electron groups. And an electron group can be either a bond or a non-bonding pair. Now, it's important to note that when you are drawing your structure out, and if you circle your region that has electrons and it's a bond, that you might end up in an interesting situation like, say, this. I'm going to circle the places where there are electrons. Here are some electrons. They're on this side. But here are also some electrons on the right. Notice that I circled all of the bonds that were connected between 2 atoms. Even though there are 6 electrons here, it's still only one group. Because it's all about where the electrons are, right? These electrons all connect to the same atom, so they're all functionally in the same place. The force of attraction that those 3 bonds create is so strong that it resists the repulsion of all 6 electrons in there. And so they all coexist in that same location to make a really tight bond, a really strong bond. Because they all exist in the same space, we're going to treat them as one group. So the number of bonds in a location between 2 atoms doesn't affect how many groups there are. It's always counted as one group. So this molecule here would be 2 electron groups. So again, any number of bonds in a, I want to say in a location, but I don't know if that's specific enough. Oh, I made the eraser really tiny too. I got to fix that. Any number of bonds between 2 atoms is equal to one group. Okay? So our goal is going to be draw the Lewis structure and then count the electron groups. That's your mission for starting out our Lewis structure geometry assessment. So again, the space that the electrons take up, we're going to call that Vesper electron groups, or just electron groups if you prefer. That's what I call it because I feel like Vesper is a little redundant. All right, we now know what groups are. And I never know why this animates on sound. I need to go fix that at some point. What we're going to do is we're going to draw Lewis structures and then assign them to a template. On the screen, you can see the shapes that can appear for the number of groups, where n is the number of groups. So if there are 2 groups, the shape that the molecule makes is a line. If there are 3, it makes a triangle. And if there's 4, it makes this tetrahedron shape. And so what we're going to do is we're going to go over to this right here. I'm going to make this a little smaller just so that we can get more space. And what I'm going to do is I'm going to draw, we're going to draw the Lewis structure of a molecule. And we're going to apply it to the template. We're going to try and figure out which shape best suits it. And it's going to be kind of obvious because you're going to look at it and be like, well, we already made it that shape, right? So the first one we're going to do is CS2. And I'm going to give you like a minute to start drawing the Lewis structure. Or 2 minutes or so. Actually, here's what I'll do. I'm going to have you draw the Lewis structures for these molecules. There we go. Okay. So we're going to start with this exercise. So just a little warm up from yesterday. What I want you to do is draw the Lewis structures for these 3 molecules, and then have them on your paper or on your tablet or whatever. And then we're going to discuss them. So like have them ready so that you can draw on them later, that sort of thing. What dictates the center purple element? The center element is going to be whichever element you would draw as central in the Lewis structure. Remember that in the in the formula, the central atom is the one that's listed first. So the purple element in the illustrations is always going to be the first element listed. That's the central atom. So first task, draw your Lewis structures for these, and then try and match them up spatially with the pictures that I've shown you. One of your Lewis structures is going to match super well, the other one's going to match very well, and then the third one's not going to match well at all. And that's going to be strange, but we're going to have to talk about it. Okay? So I'm going to give you like 3 or 4 minutes to draw these Lewis structures, maybe a little longer. And we'll go over the answers together after that. So see you in a bit. All right, so hopefully by this point, you have drawn the Lewis structures for these molecules. I'm going to go over them real quickly. So if I count the number of electrons here, I get 16, 4 from carbon, and 6 times 2 from sulfur. I'm going to draw the C in the center. I'm going to put the S's on the outside. And I'm going to connect my electrons. So 2, 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've used up all 16 electrons. I need to move some of my electrons so that they form extra bonds so that everybody satisfies the octet rule. And there you go. So I think we did this one yesterday. For CH2O, this has 12 electrons, 4 from carbon, 2 from both hydrogens added together, so 1 each times 2, and then 6 from the oxygen. Oh my goodness, all I hear are cats. My cats are screaming in the background because there's a box. I brought a box in because I got a package, and they want in the box, but they can't because I haven't opened it yet. And so I'm going to draw my connection. So 2, 4, 6, that's 6 electrons here. 7, 8, 9, 10, 11, 12. That's the remaining 6 electrons. I'm going to move some of them over to make octets. And there you go. There's my structure. And then finally for CCl4 here, I have 7 electrons for each chlorine. There are 4, so that's 28, plus the 4 from carbon is 32. And I'm going to go like this. Oops, I should have probably put the chlorines down first. So there's 8. And then I'm going to go 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I've used up all 32 electrons for my structures. All right. Now we're just going to match up the shapes. Well, let's count the places where electrons exist around the central atom. So remember, we're only doing this relative to the pink atom to figure out geometry. You could figure out geometry on other atoms, but that geometry is local to the atom that you select. For our purposes, we're always going to look at the central atom. Okay, so in this case, here's my central atom. I'm going to circle the places where electrons are around it. So I got here and here. There are 2 electron groups that I selected, and so what I'm going to do is I'm going to assign it a geometry, and I got to put those geometries on the screen here so that you can see them. So I'm going to call this linear. What that means is that these atoms are all in a straight line. The sulfur connects to the carbon, connects to the sulfur, and they are in space in a perfect line. Let's go over to the carbon. Here's my central atom. Or I'm sorry, the next picture. I have 1, 2, 3 places there are electrons around the central atom. We're going to call that trigonal planar because it makes a triangle-like shape, and all of the atoms are on the same plane. Hopefully everybody knows what a plane is. A plane is like a sheet of paper would be a plane. It's a flat surface that extends forever in every direction. But it's also only two-dimensional. All the atoms exist on that plane. And then for the fourth one, how many electron groups are there around the central atom? There they are. So for 4 groups, we're going to get something called tetrahedral. And this is the one that you're going to look at and be like, oh, wait a second, I've been drawing it like at 90-degree angles all this time. Isn't that how it's supposed to be? Like, that looks like it's the furthest apart. Why is everything all crowded? And the answer is, this is where the 3 dimensions come in. If I draw a shape like this, so here's a central atom, and I'm going to draw basically like this. The angle between these is 90 degrees. But if I draw my shape in a different orientation such that I'm using 3 dimensions, so this one is going to be flat on the paper. This one is going to kind of go into the distance in the background. And this one's going to come out at you. And it's kind of hard for me to draw that. I think I actually reversed these now I'm looking at it. Sorry, one of these will come out at you. And then the other one will be on the plane. That looks better, okay. If you do this, and you measure the angle between them, you can see that that's not 90 anymore. That's a little bit more than 90, isn't it? Turns out this is the bond angle. And when we get a larger bond angle, that allows us to have more space between the electrons, and thus is the shape that you see. So in reality, we don't ever observe this. So all these drawings that we've been doing for 4 things do not represent the geometry accurately. They are just a model. They're just our best sort of sketch. And for learning, that's fine. But now that we're talking about geometry, we're going to want to try and draw stuff that matches this sort of template. So a better way to draw CCl4 would be something like this. So the top part's fine. And then I draw one going down here. One kind of going in the back. And then one going to the side. And by doing that, I'm going to try and draw over this in a different color. Let me not do blue. Let me do like... Yeah, that'll work. Okay. That wasn't a great line. I'm trying to draw this so that you get the sense of the tetrahedron. There you go. Can you see the tetrahedron in the drawing? Hopefully. I tried to draw that the best that I could. And so that's going to match up with this diagram that you can see right there. Now, if my drawing isn't convincing enough, and I can't really criticize you for that because I am definitely an amateur artist on the best of days. What we do have here is a website that models these shapes for us. So let me put 2 extra groups in here. Let me make sure that this is capturing properly. Yeah, I gotta make this a little bigger. So this is the link that I sent you. That's everything I think I need. Okay. And so if I hit this button over here that says show bond angles, you'll notice that if I manipulate this in space by just kind of dragging it around, I don't get a situation where it looks like everything is right angles. Like if I have it like this, it kind of does look like everything is right angles, but you could tell that these 2 are closer than these 2. And if I kind of yank one of them so that it is a 90-degree angle, you can see that all the other angles respond in turn, right? because electrons repel. And so what this program is doing is it is automatically calculating the repulsion between each of the bonds. So that if I were to move something, all of the angles would then change their position relative to that until everything is equilibrium. The force on each of the bonds from the other bonds is the same. And that only happens when you have this shape. Now, if I take away one of these, you'll notice that it changes. And now there's my trigonal planar. So you can see that it's flat. Everything is on the same plane. And if I take away another one, I have linear. And there's my linear. So you can play with this by clicking on that link that I sent you. You do have to run the JavaScript application to do it. But it's a really good way to model. And you'll notice that whether I use single bonds or double bonds, the geometry is the same. Because those electrons are in the same group. So I could, and this will let you simulate it, you could just break the octet rule. You could just do something like this, right? Like, you can't make 12 bonds to something. But the geometry logic is still the same. So you can simulate any number of bonds that you want to. This will let you do that. But like, say something like with a triple bond and a single bond. We did HCN the other day, I believe, and it looked like this. So there you go. All right, we'll come back to that in a little bit. All right, so your task is going to be to assign a Vesper geometry. Oops, I didn't mean to do that. To each molecule that you draw. All the Lewis structures that we're going to draw in this class are going to fall into one of these three categories. It will be linear, trigonal planar, or tetrahedral. Now, the term that we're going to use for this geometry, because I'm about to introduce another term here, these three geometry shapes are called Vesper geometry, and other textbooks call them electron geometry. So you might see both terms, but for our purposes, I believe your textbook calls it the Vesper geometry. That's going to be relevant because in a moment, I am going to introduce you to molecular geometry, which is slightly different, and consider something else that we haven't really looked at yet. All right. This link is what I was showing you in just a second. In your textbook, I believe this is page 130. I actually don't know where the 121 textbook is. My copy is probably in this box here that I have to unpack that the cats sit on. But what we're going to do is we're going to generate a bunch of different molecular geometries that are slightly different. And the way that I'm going to explain that is, oh, shoot. First, I'm going to click over here. Hopefully you could see most of this. Yeah, we haven't really done anything other than me writing at the top there. So I forgot to click back on the lecture window. So I wrote this up here. Oops, I just erased all the text. This geometry that we were looking at is the Vesper geometry, also known as the electron geometry, from other different sources. But now what we're going to do is we're going to go back to this page here. And what I'm going to do is I'm going to start using these lone pairs here. You can't see my cursor because I'm not clicked on it. There we go. So for instance, here was a molecule that I could have drawn, and I would have 3 electron groups and it would be trigonal planar. What I'm going to do is I'm going to get rid of one of these, and I'm going to put one of these in. And what do you notice happens about the shape? Almost nothing different, right? The angle is still 120. It still looks like a triangle because there are 1, 2, 3 electron groups. One is this bond, one is this pair of bonds, and one is this electron pair, which I can like tug around like a I don't know, like the ear of a kid or something. Or their nose. It does look kind of like a snoot, doesn't it? All right. Now, very importantly, atoms, in terms of like this is the entire atom, are much larger than a pair of two electrons. So while this is the structure with the electron pairs drawn, to an observer, the molecule would look like this. And you might be inclined to say, oh, wait a second, there's only two electron groups there. The third electron group that was here is an electron pair, but electron pairs are very small compared to atoms and bonds leading to those atoms. So if you were to visually inspect it, you might say, oh, well, there's nothing here. You can see where the other atoms are and then imagine lines connecting them. But the electrons themselves are much, much smaller than atoms are. However, they still have the same influence because electrons repel, right? So even though they're tiny, they still push apart these bonds and have that space that we've drawn there carved out to themselves. And so what this shape is called the molecular geometry. Because it doesn't look like a triangle anymore, does it? It's not trigonal planar. There's only three things here, but it's not linear either because they aren't in a line. So we have to start generating shapes for all of these possible arrangements of how many electron groups are there and then how many electron pairs. So what we're going to do is we're going to create a chart of sorts on our slide here. And so what I want to do is that didn't work. Hold on. Oh, that's why. I didn't have the thing selected, so I could go like this. And then it should beep at me. Yeah, there we go. Oh, that didn't work either. Why didn't it? Oh, it did work. It just pasted it off the screen. Okay, cool. So undo. I need to make the canvas a little bigger. So give me a second here. So we're going to go like, let's just do a new image here. So new, and I want this to be really, really, really big. Okay, there we go. Okay, so here's what we're going to do. If this will work, there we go. So I'm going to make a column, number of electron groups. And then I'm going to make a sort of row going in this direction. So number of electron, or let's say not electron. Number of, oh, that's not an eraser. Why are you like this? That's bizarre. Oh, I know why. Okay, so undo. Okay. Oh, for fuck's sake. There we go. Number, no, I just did the same goddamn thing again. Okay, so number of non-bonding electron pairs. I'm going to go 0, 1, 2, and then over here I'm going to go 2, 3, 4. All right, so in this column right here on the left, these are going to be our Vesper geometries. And then in the chart that we're about to make here, so everything in this chart here, these are all going to be molecular geometries. And we're going to create those and see what shapes we actually get. And you're going to notice that for some of them, there's like absolutely no difference. So let's put this back on the screen here. What I'm going to do is I'm going to clear everything. And lone pairs are showing. Okay, cool. I'm going to check that box down at the bottom that says electron geometry. Just for information for now. All right. So the first thing I'm going to do is I'm going to make a structure that has 2 electron groups. I can pick any of these that I want. I'm just going to pick those 2. Does this satisfy the octet rule? No. So I could do this instead, or I could do these 2 instead. Doesn't matter. I get the same result either way. And so our molecule has 2 electron groups, and of those 2, oops, I can do better than that. So now what I'm doing is I'm trying to like copy and paste these so that I don't have to draw them over and over. There we go. With 2 electron groups and none of which are electron pairs, if I go down here and hit molecular geometry, it looks like the same thing that we had before, and it totally is. So the name is going to be exactly the same as the Vesper geometry. So everything that has 2 groups is going to be linear. And then what we're going to do, and this is going to take a lot of clicks on my part, is I'm going to go like this. Oops, hold on, actually. I got to copy it again. Did this paste? Yeah, there we go. Okay, so I got this, and we're going to put this right here. Oops, if I can click on that. And then I'm going to just write under it linear. All right, cool. And then we're going to go back over here, and we're going to do that again, but we're going to get rid of one of these groups and replace it with an electron pair. And you'll notice that everything is still in a line. Let me try and drag this so that it's more horizontal. We'll copy and paste it. And we'll paste it into our diagram over here. And that's going to look like that. Now, obviously, if there's only 2 atoms, it's always going to be linear. In fact, this one's just sort of to show you the concept that I'm doing here. So that one we don't really care about too much because you're not going to see 2 groups where one is an electron pair. But with 3, things get a little more complicated. So we'll clear everything, and I'll go doot, doot, doot. So I have something that satisfies the octet rule. And you'll notice down here that the electron geometry, which is the Vesper, and the molecular geometry are the same because they look identical. They're both trigonal planar. So we'll copy that. And, oops, I hit the wrong button. Paste. Oh, I could just hit Control-T to transform. I want you to link these, and I want to do this. Oops. You can't actually see what I'm doing. I'm just resizing this thing. Apply the transformation. There we go. Okay. So far, this is an exercise in, like, duh. Like, what are we doing? It doesn't make sense. But now, when we go back over to here, and I replace one of these with an electron pair, you'll notice that suddenly the terms are different. It's trigonal planar Vesper geometry because there are 1, 2, 3 electron groups. But remember, electron groups are invisible, right? So the shape that we get isn't trigonal planar anymore. It's a new shape. And the shape that we have called this is called bent. So what I'm going to do is I'm going to show all of the electron pairs in the pictures because that's what I've been doing so far. And then we'll paste this over in here. And then Control-T. And, oops, I got to do this. And so that shape is just bent. Because, and we'll draw this in red, because why not? So here are my electron pairs. I'm just going to scribble over them, kind of. And now if I were to go back over to this screen here, and I were to get rid of another one of these to replace with an electron pair, then it looks kind of vulgar. So we'll just go like this. But you can tell, duh, that's going to be linear, right? Because it's just two things in a line. So I don't really need to do that one. So there are all the examples for 2 and 3. So we'll do now we'll do the 4, and then we'll take a break. So let's clear everything. So 1, 2, 3, 4. Let me get the tetrahedron on here the best that I can. There, that looks kind of what I showed, like what I showed you earlier. So we'll copy that. And I've zoomed out a little bit. So we'll go paste. Put this down here for 4. I have all the space I could ever want, so I could just do this. And then we'll do that. The selected area is empty. Yeah, it is. Hold on, I can fix that. Oh, no, you didn't do that. How dare you. Boop. There we go. Oops. Oh, that's why. There we go. Okay. Technical difficulties. Okay. So, there's our 4. Oh, I don't want to do that. That's going to be bad, right? Let me undo. All right. So, there's tetrahedral. Let's go see how this changes when I start replacing some of these with electron pairs. So, if I go like this, boop, boop. I'm going to spin this around a little bit so that that guy's on top. And so you could still see the tetrahedral shape because there are 4 groups. But one of them is an electron pair. And when I go like this to make it look invisible, now you can see it's this little tiny squat pyramid, right? And so the shape for this is trigonal pyramidal, where you have 4 groups, but one of them is an electron pair. So we will copy and paste that. And we'll go paste. It didn't work. Paste, paste. There we go. And so we'll write down what that is. And then finally, for the last one here, we're going to get rid of another bond, and we'll put another bonding pair in like this. And so it still sort of has the tetrahedral shape in 3D, but when I go like this, now you get something that looks like that. And you might recognize that this orientation of electrons and bonds, this is the shape of water, believe it or not. You might have thought the shape of water was about a lizard, but it's actually bent, because that's what it is. So we'll copy that, and we'll put that in our diagram. And those are all the shapes that we're going to do in this class, so we're all set. And if, in case you missed the shape of that, this one is also called bent. All right, and then I'll go scribble over all the electron pairs just so that it, there you go. so that it has the same sort of theme, I guess. So your job that we're going to do after we take our break, because I went over a little bit here, is to first assign a Vesper geometry. So let's get this in, like, there we go. I hit cancel because I'm a dummy. There we go. So your job is going to be first to assign a Vesper geometry. Which family, 2, 3, or 4, does your molecule fall into? And you're going to give it a Vesper geometry. And that's going to be linear, trigonal, planar. So we'll write those down. Linear, trigonal, planar, or tetrahedral. Which family does your molecule fall into? And then you're going to count the number of non-bonding electron pairs around the central atom. It will be 0, 1, or 2, in which case you will determine which member of that family you are. So the Vesper geometry is the family. The number of electron pairs the number of non-bonding electron pairs determines which member of the family it is. So for instance, if I had something that had, let me hit this real quick so that I can draw on and erase. If I had something that had 3 electron groups, and one of those was an electron pair, so something that looked like this, its structure would be bent. If I had something that had 4 electron groups, so like maybe we'll just draw water real quick. Here's what water looks like. There are 4 electron groups. So I'm tetrahedral for my Vesper geometry. How many of those are electron pairs? 2 of them are. There's the molecular geometry of water. So that's what you're going to be doing when we get back from the break. So if that's a little bit overwhelming, that's okay. I'm going to give you 10 minutes to just like take a breather, go get some water. You can rewind the video a little bit, go over how I acquired these pictures, play around in the PHET simulator. And we'll discuss it more when we get back. If you have any questions, let me know in the chat. So we'll put this up here, and we will get the music going, and I will see you in just a little bit. Hi, we're back. All right, so we've got all our geometries on the board here. So I'm going to keep this image for the rest of the lecture here. Oops, hold on. Computer's getting upset with me because I clicked where I shouldn't have on the YouTube music. There we go. All right, so I'm going to keep that handy for the rest of the lecture here because we're going to be using it quite a bit. So let's go back over to this screen. So we've generated this chart. And so again, I told you how to use this chart already over here, where step 1, you assign a group for a Vesper geometry. You count the number of electron groups for Vesper geometry. And then you count the number of non-bonding pairs to determine the molecular geometry. Here on the slides, I've added a step 0 of sorts, which is draw the Lewis structure. You do have to do that. And you want to draw the Lewis structure as accurately as you can with geometry considerations in mind. So if it helps you to draw stuff in like 90-degree angles, then that's fine. Because I'm not going to be assessing your pictures. You can't turn in a picture in this class. But it's important to keep in mind that there are no 90-degree angles in Chem 121. So those are actually secretly tetrahedrons. So, all right. So what I'm going to do is I'm going to have you draw a molecule. I'm going to have you draw ammonia first. Sketch out its molecular geometry, or I'm sorry, sketch out its Lewis structure, and then I want you to tell me both its Vesper geometry and its molecular geometry. And we'll go over that answer together in about 2 minutes, okay? So draw the Lewis structure and then use that chart. In fact, what I'm going to do is I'm going to put the chart back up on the screen so that you have it. And we'll go over the answers shortly. All right, hopefully by now you have drawn the Lewis structure of the molecule. And I'm going to draw that on the screen in a second, too. I'm trying to fix something real quick. There we go. So I need to go over here. All right. So I'm going to, in the top right corner here, I'm going to draw my Lewis structure. So let me get a color out that's not any of these. So we'll do blue. All right. So for ammonia here, so 5 plus 3 times 1 is 8 electrons. And you should have gotten something that looked like this. So there's our structure. Now we need to figure out how many electron groups there are. So how many places are there that are electrons? 1, 2, 3, 4 electron groups around ammonia. So our Vesper shape for ammonia is tetrahedral. Of those 4 groups that we circled, how many of them are electron pairs? 1. So that means we're this one. And so the molecular geometry is trigonal pyramidal. So if I was to take this little picture down here, and I guess we could zoom in on here. Here's what ammonia would look like. So the nitrogen would be in the middle here. Here's a hydrogen, here's a hydrogen, here's a hydrogen. Electron pair. There you go. That's how it would look. So after you've drawn your structure, once you've selected a model for it, you should be able to draw the model over it exactly. All right, now let me do... Oh no, I drew on the wrong layer. Oh, I've done every Photoshop artist's worst nightmare. How far back does my history tool go? Far enough, thankfully. Okay. Hold on, I have to fix that. So if I do... Yeah, that's fine. Okay. Please be on the correct layer. There we go. Okay, now I have the correct layer, so the next time I use this, I won't permanently ruin the molecule, or the paper. Okay. All right, so same thing with CO2. I'm just going to give you the answer for CO2 because I want to get to the examples here. So I'm going to give you about 5 or 6 minutes to try these. I'm going to put them back on this screen right here. So we'll just do that. Hopefully those are big enough. Yeah, that's good. Okay, so there are our 4 practice molecules to draw. I want you to draw these 4 molecules here, and I want you to assign them a Vesper geometry and a molecular geometry. Type your answers in the chat once you've got them, like what's the Vesper geometry, what's the molecular geometry. Do the best you can. 5 or 6 minutes is not going to be enough time to actually do that. But we'll go over all the answers together in just a bit. All right, 1 or 2 more minutes to do as many of these as you can, and we'll go over the answers together. If you have any answers at all, type them in the chat for me, and we'll go over them shortly. All right, let's go over the answers here. So the way that I'm going to do this is that top right space on the board here. I'm going to try and so this region right here. I'm going to try and put my Lewis structures in that space. And then we'll just draw all over the place. Make sure I'm on the right layer here. All right, so for ozone, this is 3 times 6 electrons, which is 18. Hopefully by this point, I don't need to explain how many electrons these things have. But I'm getting this from the groups one last time. So oxygen is in group 16. Each has 6 valence electrons. There are 3 of them. So I'm going to put them all, I'm just going to put them all in a row for now because I don't know what the structure is going to be, right? So I'm going to connect them. So there's 2, 4. And then outer octets 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 18 electrons, but I am missing an octet on the central atom. So what I need to do is I need to go like this and make a double bond. Now, does it matter what side your double bond is on? No, it does not. Interestingly enough, ozone isn't symmetrical. You might think it is just by looking at the formula. It's got 3 O's in it. But it's not symmetrical in terms of our structure. Now, if you go look up more advanced videos, you'll learn that the Lewis structure for ozone is not great and that it actually is symmetrical. But there are weird things going on with it. For the purposes of this class, that structure is correct that we have drawn on the board here. So don't worry too much about the fact that it looks odd. What we should be more concerned about the fact is that I have drawn it in a straight line, but there are very clearly 3 electron groups around the center, which means that it should be trigonal planar. So a better ozone would look more like this. And then I'll put the electrons on the outside here. So that's a better drawing. So sometimes your drawing may not match what the actual geometry is. And of those 3 electron groups, 1 is an electron pair. So ozone is trigonal planar and bent. All right. All right, let's do the next one. So I've got SnCl3 minus. The minus is important. So we've got 4 plus 3 times 7 plus 1, which should be 26. All right, and so I get something that looks like this. This one I am going to draw correctly because I actually know what the answer is. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Wait a second, what is tin doing? Tin's a metal. How does tin form covalent compounds, you might be asking? Which is a good question, it turns out. Why the heck is tin in here? Turns out that there is a little bit of a gray area with covalent bonding that we're going to talk about in like 3 slides. And we'll see that in just a second. For now, just run with it. So there's my Lewis structure. How many electron groups are around the central atom? 1, 2, 3, 4. So this is tetrahedral. Of those 4 electron groups, how many are electron pairs? 1. So there it is. And so you can imagine my drawing superimposed over that. All right. So now we'll do selenium dichloride. Uh, 20, I believe. Yeah. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There you go. How many electron groups are around the central atom? 1, 2, 3, 4. So it's Vesper's tetrahedral. Of those 4, how many are electron pairs? 2. And so you can imagine its geometry right there. All right, we'll clear that one away. That didn't work. I don't know why it didn't work. Let's fix that. There we go. All right, finally we got carbonate. So 4 plus 3 times 6 plus these 2, 18, 22, 24. So we got 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. This one kind of didn't show up. Don't have an octet on the central atom, so I'm going to erase. Oops. I'm going to erase. There we go. And then there's our structure. All right. How many electron groups are around the central atom? 1, 2, 3. So its Vesper geometry is trigonal planar. Of those 3, how many are electron pairs? None. So its molecular geometry is also trigonal planar. All right. I hope that has helped explain how we determine the geometry. That's a lot of work, right? Like, that took us 90 minutes to do. So make sure that you are doing the homework practice for this section, because this is a complex topic. And we're going to use it immediately in the next section when we talk about polarity. So, all right. Speaking of, let's go to the next section. So, we're not going to be able to finish this today, but thankfully tomorrow is a review session. I can appropriate part of it as the rest of Chapter 5. So, we're not going to rush through this. We're going to try and do this correctly. All right. On the previous slide, back here, I sort of just gave you this Lewis structure without saying anything. And then when I drew it on the board, I was like, wait a second, that's a metal. How can a metal have covalent bonds? Shouldn't it be ionic? And it turns out that chemistry is not a black and white science. A lot like everything. It's very difficult to compartmentalize anything in the science, or like anything at all, really. This is just a general philosophy for life. It's very hard to compartmentalize things into 2 distinct, discrete categories. There's always going to be something that sort of straddles the line, that falls in the middle. And the property that we're going to talk about right now, electronegativity, governs how the extremes work, but also that gray region in the middle. So you already know that covalent bonds share electrons, and that ionic bonds transfer electrons from the metal to the nonmetal. Now, the question that I have for you is there a sort of in-between state where we have in-between sharing and in-between transfer? Like, we share part of the time, but then we have to slowly give it up. Yeah, it's called rent, right? Where I get to stay, but I have to pay a part of my money every month, and all I get back is staying in this place, right? Yeah, rent is awful. So the in-between state is going to be sort of a gray area. It sort of behaves like covalent, but it sort of behaves like ionic. Stuff is shared, but it's also transferred partially. What the heck does that mean? Let's investigate it further. On the board, I have 2 chlorine atoms in a bond. And if I was going to draw where the electrons would spend most of their time, you would just say, well, in the bond, right? Because they're bonded, right? Now, the electrons in the bond are not immobilized. They can move around like all the other electrons do in their own sort of electron cloud between the 2 atoms for their bond. But both of the chlorine atoms have a nucleus which is positively charged, right? And that nucleus is going to try and pull the electrons in the bond towards it. Now, my question for you is, who is going to win here? Oops, I didn't mean to do that. Chlorine or chlorine? Who will pull the electrons towards their nucleus the most? And hopefully you're sitting there going, well, duh, nobody's going to win. They're both chlorine, right? They're exactly the same. And that's correct. So in a chlorine molecule, or any molecule where the atoms are just bonded together and the atoms are identical to each other, the electrons are going to be evenly distributed along that bond. They're going to spend an equal amount of time at any given location in the bond. But what if I do this? Do chlorine and hydrogen want the electrons the same? Well, I know that chlorine has 17 protons in its nucleus, and hydrogen has 1. Who's going to pull harder on my electrons, 17 protons or 1 proton? And the answer should be pretty obvious. Like, yeah, my electrons are going to get pulled in this direction more than they're going to get pulled in this direction. They're going to get pulled a little bit to the left, so they're not going to completely get transferred. Another way to think about this is to think about it in terms of charges. Cl likes to be Cl minus in an ionic compound. We haven't really talked about H+. It turns out it does exist. We'll talk about that in chapter 10. Could I make this an ionic compound? If I gave all of hydrogen's ions or electrons away? I could. Then it would have a positive charge, and then it would be attracted to the minus, right? So now, because they're both nonmetals, I've been telling you that this bond is covalent. And it is, but it's also not quite covalent. It's somewhere in the middle of covalent and ionic, because the electrons are pulled towards chlorine much more strongly than they're pulled towards hydrogen. So we would say, on average, the electrons are closer to chlorine than hydrogen. Hydrogen gets to see them a little bit of the time, but not all of the time. You could think of it as like, if your work takes you away from home for long periods of time. So like maybe you have to like fly to England or something to do your job, and you're regularly across the sea. So you don't get to see the kids as often as your spouse does, or your partner, or what have you. The kids are closer in proximity to your spouse than they are to you, but you do get to see them enough. You don't transfer the kids. You don't just give your kids away. You both still have the kids. It's just that one person has them more often than the other in terms of time and distance. And that's what's happening here. Think of the electrons as the kids. Chlorine is watching over them more closely than hydrogen is, because hydrogen had to go fly across the country. or something like that, because their job took them far away. That was the best analogy that I could come up with when I quickly trashed my analogy of, let's say that you and your partner are divorced and someone has custody. I was like, that's too dark. I don't want to talk about that. Let's do something happier. Yeah, you just have to work. Turns out work is not happier. Dun, dun. Anyway, we're going to quantify this property. How well do atoms pull electrons towards themselves? We're going to call that quantity electronegativity. So electronegativity is the ability of an atom to pull electrons through the bond. Atoms with higher electronegativity are stronger. They're going to pull the electrons closer to them. Now you might think, oh, this is going to be easy. I'm just going to count protons. Well, it turns out distance is important too. Small atoms get the electrons closer to the nucleus and have a higher pull. So we have to take into account size and number of protons. And so we don't really talk about atomic size in this class very much. It's sort of beyond the scope of this class. We talk about it in engineering chemistry. But we're going to just summarize all of the traits that somebody is analyzed and compiled together as this term, electronegativity. And we're going to assign an electronegativity for every atom on a scale from 0 to 4. 4 is the most electronegative. That means that if you are an atom with electronegativity 4, you pull the electrons stronger towards yourself than any other opponent. If your electronegativity is 0, then you have no pull at all, and you just kind of give up your electrons like a wet noodle would. I don't know. Now, I have a chart. There's a chart in your textbook. It should look similar to this. And this chart labels all of the electronegativities of the atoms that have been measured. You'll notice that not all atoms are shown. For example, the noble gases are not shown. This is because they don't form bonds, so we can't measure their electronegativity. Other electronegativity tables will have different numbers. Use this one or the one in your textbook. They should be similar. Close enough for our purposes. And what you'll notice is that as you go from left to right, electronegativity tends to go up. So the low end is over here, and the high end is over here. You'll also notice that as you go down a group, electronegativity decreases. So this is the low side, this is the low end, and this is the high end. So the most electronegative element is fluorine. Fluorine is the best at pulling electrons towards itself because it has a large number of protons for its size. If you go to the next row, chlorine is very good at pulling electrons towards itself, but because I've added that extra shell of electrons, because it's in period 3, those electrons are further away, and it's harder to hold on to them. So size matters in terms of electronegativity. And as you get a bigger atom with more electron rings and orbitals around it, it gets harder and harder to hold on to that many electrons because they're so far away from the nucleus. So those are the features of electronegativity. What we're going to do is we're going to use these numbers as a comparison. I'm going to compare the two electronegativities of my atoms. So if I bond hydrogen and fluorine, I'm going to compare those two. And the difference, or delta, is going to be just whatever it is that I calculate between them. So the difference between 2.1 and 4.0 is 1.9. Okay, for example. All right. There's our summary. Electronegativity increases if you go up or right on your periodic table. It decreases if you go down or left. And then there's some general trends. Because all the metals are on the very far left, they tend to want to give up their electrons anyway. Their electronegativity is very low. Nonmetals, on the other hand, want electrons because they want to complete their octet. They're close, yeah? Metals want to ditch their electrons. So this all jives with our understanding of how atoms want to form octets. We're just assigning all of the things that we've discussed so far a number. All right. The last thing we're going to do is we're going to apply this to create a term called polarity. So polarity is, if I go back to this description right here where I had my H and Cl, polarity is how far are my electrons unevenly shifted. Something is polar if the electrons tend towards one side more than they do the other side. If something is polar, and I will say, okay, I'm more likely to find the electrons on the right side, what I do is I write this symbol. I write a delta, and then I put the sign of the electron if there's more electrons on that side. Or I put the sign and a positive if there are fewer electrons on this. So this is called polarity. Think of polarity as a partial charge. So instead of having a minus charge on chlorine, I have like half a minus or a third of a minus or something like that. It's a fractional charge. There is some charge there, but it's not one, as if I just gave the electron away and it lived there forever. Polarity is just going to be a measure of how far over are my electrons most of the time. You could also think of it as a percent, for example, if that helps you. For instance, if you are away from home on your business trip 15 of the 30 months, 15 of the 30 days in a month, you would be around your kids for only 50% of the time. That analogy isn't going to work. You're not around them 50%. 50% is much. In terms of raw time, you'd be spending like a quarter amount of time, I guess I would say. Because your spouse would be with the kids the entire time, whereas you're only with them for a fraction of that. So you could think of it as a percentage. Oh, you're here 50% more than I am, or something like that. The way that we're going to determine if something is polar or not, we're going to look at those electronegativity numbers. If you compare two atoms together, oops, not H. We're not going to do H. I'm trying to think of two that are different by. Oh yeah, no, we are. We are going to do H. And I have most of the numbers memorized, just because I have nothing better to do, I guess. I don't know. If I compare two atoms and the difference is 0.4 or less, it says less than. I'm going to actually strike this because we're going to write it like that. Mostly because the CH bond is considered to be nonpolar in organic, and it's very important that we say that. Your textbook says this, but I'm going to just say no, don't do that. If the difference is 0.4 or less, we're going to call it nonpolar. If the difference is between 0.4 and 2, we're going to call it polar. The term covalent is just to indicate we're still sharing electrons. Nonpolar covalent means we're sharing them equally, virtually equally. The electrons are right in the middle. Polar covalent means they're shoved off to some side, like with HF or HCl, like I just showed you. Now, this statement is not universally true. So I would actually almost want to say do this to it. I'm modeling these slides after your text and then making edits. For our purposes, 95% of the time, that will be true. If you see a metal, the bonding is ionic. But with the tin example, for instance, it is covalent. You're not going to be tested on that, though. Don't worry. The last thing that we want to consider, I got to move this out of the way here, is what happens if the difference is greater than 2. If the difference is greater than 2, then the electron is essentially transferred completely away from the first atom and given to the second atom. And that's what we would call ionic. So when we come back tomorrow, what we're going to do is we're going to look at a series of molecules, and we're going to try and assign them a polarity. We're then going to take Lewis structures and draw those with pictures. And then the last thing that we're going to do is we're going to turn that information towards an entire molecule and determine, is a molecule polar or not? And then finally, when we come back on, finally, we're going to learn how to name covalent compounds, which should not take very long at all. So that is all the time that I have for today. So we're going to go back to the title card here. I do want to thank everyone for coming to the lecture. Make sure that you get quiz number 3 in if you haven't done so already. It is due by the end of the evening. And then quiz number 4, or I should say quiz number 3 is closing tonight. Quiz number 4 and lab worksheet number 2 are also due tonight. Those close tomorrow, just in case you don't have enough time to get them in. We'll have a lecture tomorrow /review session. Please bring questions that you might have for that. And I'll see you then. Take care.